error control codes, block codes, basic concepts and definitions. Let me repeat encoder channel decoder system, starting from channel encoder. We assume that we are dealing with a binary code, fixed length binary code. So the source encoder produces information, code word, and then channel encoder produces a code word. For the given information word, the parity check bits are calculated to give the code word. Then these code word or code words are transmitted through noisy channel. Error patterns are added to give the output sequences and output sequences. And in channel decoder, the decision whether the obtained sequence is a code word or not. If not, then the correct or detect is taken. Classification of error control codes. I will be dealing only with binary codes and block codes, linear codes. We will discuss during the presentations error correcting codes, Hamming code and cyclic codes, error detecting codes, single parity check code, and other codes will be not discussed. This slide presents once again the source channel encoder, source encoder, channel encoder, channel decoder, encoder, source decoder system. But what I would like to repeat, that in channel encoder the input is information bits, and channel encoder calculates a parity check bits and add them to information bits to create a code word. A code that generates n code words with k information bits is referred to as an nk block code, where n is the block length, a code word length, and k is the information part length. Number of parity check bits, m, is n minus k. And there are m to the m is number of messages, m equal 2 to the power of k code words. Information code words and code words of the given code. This is repeated. This reasoning information bits, and then we calculate parity check bits to obtain code words. Classification of transmissions. The total number of code words already mentioned is 2 to the power of k. Total number of error patterns is 2 to the power of n minus 1, because all zero is not all zero. Error pattern is not an error. The total number of outputs, output words, is 2 to the power of n, with m code words among them, and the rest, the remaining words, are referred to as the redundant words, and thanks to them we may detect and correct some errors. This is an exemplary code 3.2, which means that we have 4 messages. The number of 4 messages for code words, and number of output sequences is 8. This is the input for code words, and this is the output for code words plus some redundant words, a combination of zeros and ones of the length 3, but not being the code word. The errorless transmissions, denoted here in green by green lines, 4 is the number. Undetectable errors. If one code word becomes another code word due to the error pattern, then obviously such an error is undetectable, and there is 12 undetectable errors for these codes. The remaining errors are detectable errors, so it is 16 detectable errors. They are denoted here by blue dashed lines, and 4 of them are correctable errors. For example, every redundant word is assigned to one code word. For example, this redundant word can be assigned to W1, this word can be assigned to W2, this redundant word to W3 and this to W4. Very important definition, basic definition of block codes. Hamming weight, or simply weight of a word or just sequence, is defined as a number of non-zero entries. Hamming distance between two words of the same length is defined as a number of bits in which they differ. If both words belong to the same set, for example, set of code words, then we will use this notation d sub ij. And finally, code minimum distance is the minimum over all Hamming distances of the given code and designates code ability to correct and detect errors. It will be discussed later on. This is an example. A code generates these 4 code words. They are aggregated in this table. In this column we have weights of these 4 code words, and in this table here we have a Hamming distance. So for this and this, for these two, we have a Hamming distance equal 4. For all other, we have distances aggregated in this table, as can be seen. The distance is 3 or 4. The minimum distance then is 3. For this code, the minimum distance is 3. Decoding strategies. First, error detection decoding. We assume that we are only detecting errors, not correcting. So simply we check whether the received word is a code word. If so, then we set W star V. If not, then W star the question mark. Error correction decoding, a minimum distance decoding. If received sequence is the code word, then okay, W star is V. But if not, we are looking for a code word that has a minimum distance to the received sequence, the Hamming distance. And we set W star Wi, where Wi is the code word which has the minimum distance to this. This minimum distance decoding is also known as nearest neighborhood decoding. An example, same for code words. Let me assume that we have these 2 words received. We are calculating distance, Hamming distance, between the received word and every word of the code. For the first transmission we have 2, 3, 2, 3, which means 2 is the minimum. As you can see, the unique error correction is impossible. It is either this code word or this code word if we have received this. If we have received all one word, it means that these are Hamming distances, and there is distance of 1 between this and this code word. Unique error correction is possible. Error control limits. Error detection limit T sub D. The minimum number of errors that a block code can detect. To detect every single error from the total of n single errors, the minimum distance should be 2. To detect every single and double error, then 3. And to detect all errors up to T sub D, the minimum distance should be at least TD plus 1. Next, limit error correction. Limit the maximum number of errors that block code can correct, related with the minimum distance. To uniquely correct every single error, the minimum distance should be 3. As a single error added to a code word is uniquely correctable if the resulting received redundant word is closer to W sub E than any other code word. If the distance is 2, then single error or errors added to these 2 words may result the same redundant word. Then to correct all errors up to T sub C, the minimum distance should be greater or equal to TC plus 1. Also, it is possible to prove that the block code of a given minimum distance can jointly correct TC or less errors and at the same time detect more TD or less errors if this inequality is satisfied. Next presentation, linear codes, generator matrix and parity check matrix.